So, hi guys, we will try to solve this question from uh this question from NBHM. This question came in NBHM 2024, like this is a recent question. So it's question number 23, as we can see from here. Now it says like the given is F is a finite dimensional vector space, right? Uh, over F, like over F, and here T belongs to like T is a linear operator basically. T is a linear transformation from V to V, and our first option is given that if the underlying field is R, so if the underlying field is R, and for all T invariant subspaces W, so for all W T invariant, right, trace of T restricted to W is 0. Right. It says that it will imply that T is nilpotent. This is, I think it's clearly false because, right, let's say, let's just take let's say, minimal polynomial of T with uh, a minimal polynomial of, let's say, T to be x squared plus 1. And we know that this is irreducible. This has roots I and minus I. So basically, since it's of degree 2, this is irreducible in Rx, right? So this is reducible in Rx. Now let us just write the companion matrix for this. So with respect to the standard basis, this will be 0, right? Since x square plus 1, so this will be basically x square plus 0x plus 1. So this will be minus of that, and this will be 0, and this will be 1. Now as we can see, the trace is 0. But does it actually satisfy our like hypothesis that like trace of T restricted to W for all W T invariant subspace should be 0? And this is actually true because I mean if the minimal polynomial is this, if the minimal polynomial is this, now I mean in this in in this operator, I mean T is this operator, right? So I mean, there will be no non-zero proper invariant subspace of T, uh, right? I mean, of V, right? Because I mean, we already know that if T is actually a linear operator, then kernel T, let me write kernel T and image T is T invariant. Okay. Now here kernel T is actually 0, as we can see from the matrix that yeah. So this kernel T is actually 0, and since it has, I mean, rank of rank of T is 2 and image T is the whole space. I mean both are T invariant. I mean there will be uh, and and we also know that T restricted to image T, I mean the trace, that is 0, right, as we can see from the matrix. But apart from that, right, and of course for the kernel T this will be the same. Apart from that, there will be no proper non-zero proper invariant subspace. So our hypothesis is true, but like that T is not nilpotent. Okay, so it satisfies everything, but T is not nilpotent. Why say W is a proper, let's say non-zero proper subspace, I mean which is T invariant, then minimal polynomial of T restricted to W will actually divide, we know this, right? It will actually divide min Tx, but this is actually x squared plus 1, and that is not possible, right? So there will be no proper non-zero proper T invariant subspace. The only T invariant subspaces will be actually this, the kernel of kernel T and the image T, which is 0, kernel T is 0 and image T. And image T we know the whole space, so yeah. And T restricted, I mean this is the trace is 0, but T is not nilpotent. So basically our first option is false. Now, right now, okay, what about the second option? Now, the thing is same, except that it's given that the underlying field is, I think, C. It's given for the second option, F is given to be C, which we know to be algebraically closed. Now, C is algebraically closed, so we can actually write we can actually write the minimal polynomial of, I mean, it will look like this. Minimal polynomial of T will actually look like this. Um, X minus lambda I, let's say I. Uh, sorry, let's say x minus lambda I, let's say, mm, let's say R1. I mean, lambda 1 x minus lambda 2 R2 and so on, and something like x minus lambda k, let's say RK. Since f is algebraic closed, right? So our minimal polynomial will actually look like this. Now, let's say Wi. I mean, this is actually the primary decomposition theorem. So let's say Wi. So Wi to be the kernel of t minus lambda I, right, to the power Ri, right? Let's take Wi to, and we know that Wi is t invariant, right? Wi is t invariant, okay. But in our hypothesis is given that trace uh, of t restricted to all in, so here Wi, this will be 0, right? So which is given from our, for any w, for all t invariant subsets of w. So this will be 0 for all I. I mean, okay, so this will be 0 for all I belongs to 1 to k, right? 0 for all I belongs to 1 to k z. So the trace is 0. Now we know from the our primary decomposition theorem that, right, min t restricted to wi, basically x, is nothing but basically it's, yeah, so x minus lambda I to the power ri, right? So this will be the case, right? But it says the trace is 0 for all t restricted to wi. So basically lambda I will be 0 for all I belongs to 1 to k. So basically, so basically, so basically each, so basically t is nilpotent. Okay, let me go through this again. Right. So we can write W minimal polynomial of T as this, and Wi we know this kernel, and we know from so this will be T invariant, and this we all know this due to primary decomposition theorem. We can actually write V as direct sum of W1, W2, and so on. So Wi is T invariant, and it's given that for all in T invariant subspaces trace is 0. So this is 0, and we know minimal, and since trace is 0 of each t restricted to wi, and we know the minimal polynomial of t restricted to wi is this, and since trace is 0, so basically this lambda I, are one number of times their sum is 0, which means each lambda is 0. Okay, so if each lambda is 0 for all I belongs to 1 to k, then basically its t is nilpotent, right? So basically we are done. We can also see it like this. I mean, there is no space here. So let me go to another page. We can also see it like this, right? So basically, like what was our minimal polynomial of t? It was, right, it was x minus lambda I, sorry, lambda 1 r1 and x minus lambda k rk, and we know that, uh, and since it's c, since of course c is already closed, we know that this was our minimal polynomial. So basically t is triangle level, right? T is triangle level. So basically we will get a chain like this, like 0 v1, right, uh, of in t invariant subspace v1 v2, v1 v2 v3. I mean, this will be upper triangular. We can write this upper triangular, lower triangular. So we will basically get a flag like this, and so on, of t invariant subspaces, right? So of t invariant subspaces, right? Now basically, now each, for each restricted total, this is trace is 0 given, right? For this, so basically t restricted to v1, this the trace is 0. Right, so basically here the eigenvalue for this will be 0, and similarly for this. So basically we will get a matrix like this, 0, 0, 0, where each diagonal, basically since it's upper triangular, right? So the diagonal elements will give us the eigenvectors, sorry, eigenvalues. So each will be 0. So for this eigen, this will be 0, and for like this should be like this. Subspace spanned by v1, v2, v3, v1. So So similarly for V2 that will be 0, V2 will, so yeah, for each invariant, so yeah, so this will be 0 and we will have elements here, so the trace is 0. So this will actually be a nilpotent, right? Nilpotent matrix. So yes, maybe we can also think of it like this, um, or we can think of it in this way. So yeah, so this option is true. So this is a solution.